welcome back. So we're skipping part 7.4 in the textbook that talked about the finite population correction factor. I'd encourage you to read over that, but I'm not going to spend time going over it. It's not really my main point of this chapter. So now we're getting to what I really find exciting and interesting about this chapter is using statistics for quality control. Now, obviously, we're going to use statistics for a lot of different things, but one of the things that we can use them for is keeping our quality control in check. And so two ways that we're going to do that is what we call acceptance sampling and detection approach. So acceptance sampling, is used at the completion of the production process. For those of you who have taken a managerial accounting 2302, this is we're talking about one of those internal failure costs. If you haven't taken accounting and you don't know what I'm talking about, don't worry about it. You'll get there eventually. So this is when the product has already been completely produced, and we're checking it before we sell it to customers to make sure that it is correct and that it's not damaged or defective in some way. Now, certainly we want to do this kind of quality control, but it's expensive because now we've already made the mistake and we have to either throw the product away or we have to pay to go fix it. This costs time, this costs extra money, and we're not guaranteed to catch all of the defects. So just because we caught one in our sample doesn't mean that there's not some that already gone out, which can of course lead to an external failure cost, which is even more expensive. So what we'd really like to do is what we call detection approach, or again, for those of you that have taken managerial accounting, this is the prevention portion. And this is where we're sampling all along the way. And we're really checking to make sure that our production processes are correct, that they're not causing any defects, so that if we find a defect, if we start seeing that this is trending that way, then we can fix it. And so we can fix it now before we've made any more mistakes, before any more defective products have been produced. So this is a way for us to, again, check all along the steps of the process by randomly sampling what's been done and allowing us to check to make sure that maybe the machine we're using is starting to break down. But if we can catch it now at this step of the process, then we can fix it before it gets all the way to the end, and then it's much more expensive to fix. Now, we do expect some variation, and part of that is just due to chance. You know, even machines aren't letter perfect all the time. So we do expect, again, some chance variation, that not everything is controllable by an individual worker, or like we said, a machine. Even a machine is not exactly perfect all the time. So we have these limits that we'll talk about, which these are the acceptable limits of where there's some variation. Now, assignable variation is things that are outside of these acceptable limits. They're not just due to chance or to randomness. They're due to things that can be fixed. So, for example, a machine is out of alignment. We can fix that and bring these observations back into, bring our production process back into within those acceptable limits. So when we are, this is really what we're looking for, so that we can fix this before, again, we make too many mistakes. Now, we can do this by using control charts. Control charts are just a line graph. In fact, we're going to use it in Excel. So I hope you've got your Chapter 7 Excel spreadsheet open with you. So we can do this in Excel. We're going to graph our observations, and we'll calculate our upper and our lower limits, and then we'll be able to see from the graph if it's out of control, if it's still in control but it's trending out of control, or if the variation is just due to chance. So for quantitative data, we've got a couple of different charts that we can use. The X-bar chart, remember, is the mean. So this is monitoring the central tendency, or the mean, of the production process. So one of the examples we're going to look at is a machine that is filling jugs with milk, and we're measuring the mean of how much milk is put in the jug. Ideally, all the jugs would be filled with exactly the same amount of milk. But we know that that doesn't happen. And so we're measuring, we're sampling, and we'll take the mean of those samples and then graph that. The R chart and the S chart are used to manage to monitor the variability of the production process. So we're looking more at like that standard deviation, the variability of it. And then for qualitative data, we can use the P chart or the P bar chart, which measures the proportion of defects or whatever characteristic we're looking for, or the C chart, which measures the count of defects. So we may count it, and we'll want to make sure that that count of defects is within the normal range. So let's just talk about the X bar chart. First of all, they all follow basically the same process. So the center line for the X bar chart will be the mean. So whatever the mean is for the population, so mu, that's the center line. The upper limit is 3 times the standard error or the standard deviation from the mean. And so anything that is above the upper limit is out of control. And then the lower limit is 3 times the standard error below the mean. So anything falling below this is again out of control, and therefore we need to fix it. Now we're going to jump back to just a second. We kind of talked about this in our second video, but I kind of skipped over this part of it because I knew we were going to touch on it here. So remember, we're talking about the mean and the standard deviation of all of these samples that we're taking. So the variance of the sample, the variance of the sample mean is the variance of X bar, which is the sigma squared, or the standard deviation divided by n, where n is the sample size. So therefore, we can also take the standard deviation, also called the standard error, as being the sigma divided by the square root of n, where n is the sample size. So here we have an example. We are again filling jugs of milk. Every hour we sample 25 jugs of milk. So for our last 6 samples, we have values of 128.7, I'm assuming that's ounces, 128.4, 128, 127.8, 127.5, and 126.9. So we can see that they're all fairly close. They're all clustered right around that kind of 128 area. And we see that according to the machine, according to lots and lots and lots of data that we've taken over years of taking these samples, we've decided that the population parameter, the population mean, is 128 ounces, and the standard error or standard deviation is 2. So 2 ounces on either side of that. So based on this sample, the last 6 samples that we've taken, we're going to assess to see if the machine is still functioning properly. So the first thing that we're going to need to do then is calculate the standard error or the standard deviation. So here we have, remember, our mean is 128. And again, the sigma, or the standard deviation of our population, is 2. So first thing that we need to do is calculate the upper limit. So then the upper limit is mu plus 3 times the standard error. Now, since this standard error of the standard deviation of 2 is for the population, we have to calculate the standard deviation of the sample population, the samples that we've taken. So that is the 2 divided by the square root of n. Now, since we are sampling 25, then n is 25. We've taken 25 samples every time we take a sample. So we can say our mean of 128 plus 3 times 2 divided by the square root of 25 is 129.2. So that is our upper limit. Anything above that is out of control. Our center line is the mean of 128, and then our lower limit is the mean minus 3 times the sample standard deviations. So that is 2 divided by the square root of n again, which gives us 126.8. Now we're going to jump over to Excel and look at these calculations in Excel and then also look at how we graph them. So again, I hope you've got your Excel spreadsheets open. If not, open it with me and let's look at this together. All right, so here we are in our Chapter 7 Excel, and it's a little hard to see down here, but I have the milk window open. So we've got our 6 samples and our 6 sample means already plotted out for us. Now, first thing that we want to do is calculate the upper and lower limit. I know that we already calculated it by hand in the slides, but let's go ahead and calculate it here in Excel as well. So I'm just going to type this in here. Let's do this up here. I'm going to put the upper limit right up here, so I'm going to call that UCL, upper control limit. And remember, our formula for our upper control limit is the mean, which we were given as 128, plus 3 times, so I'm going to use the asterisk to mean times. Now, when we put these formulas in Excel, remember, we've got to remember our order of operations. We've got to use lots of parentheses. So I'm going to have to open some parentheses here, and I'm going to say our standard deviation of 2 divided by the square root, SQRT, open, of 25, close those parentheses. Then I'm going to close the second set of parentheses that I've opened, and that gives me 129.2. Now, I'm going to go ahead and create a chart here that I can drag all the way down. So I'm just going to drag this down, and notice that number copies all the way down. Now over here, I'm going to do the same thing. I'm going to calculate my lower limit, so LCL. So this is again my mean of 128. Now it's going to be minus, because I'm subtracting, 3 times the standard deviation of 2 divided by the square root of 25, close 2 sets of parentheses. And the good thing is, if you don't get all of your parentheses quite closed right, Excel's really good about asking you, correcting it for you and asking you if that's okay. And so guess what? We get our lower limit of 126.8. And I'm going to drag that down. And then here in column D, I'm going to put my center line, which is my mean of 128, and it's 128 all the way down, so I'm going to drag that down. Now, if I wanted to graph this now, I can just grab all of these cells from B1 through E7, grab them all. I'm going to go up here to Insert. I want to insert a line chart. And really, I want to insert a 2D line chart. Now, we can pick which one we want to insert. I'm going to choose the one with markers because I think that one's the most interesting looking. But here I've got my chart, and my chart's a little big. Let me make it a little smaller so it fits in the area here. But now I can see my upper limit is in purple. My lower limit is in red. My center line is in green. And then blue are my observations. Now, as we look at this, notice that all of the observations are within the acceptable limits, which we could tell that even without graphing it. We could tell that all of the observations were within the acceptable limits. But one thing that we can notice is that they are trending down. So this is a clue to us that, oh, we better go fix our machine. Looks like it's out of alignment, and we're getting ready to have some jugs of milk that are underfilled because we can see that line is trending down. A normal line would have, just points here, and they would all just kind of zigzag across the mean. That would tell us that the variations were only caused by chance. But here we see a trend line that we really don't want to see. That's not what we want to see. So let's jump back over to our PowerPoints now and continue looking at a different chart. So again, we've talked about the P charts. They measure the proportion of defects. And so again, we're going to have to calculate the sampling distribution of the sample proportion as well. And we looked at that in an earlier video, but we'll look at that here again. So So again, the center line is this expected proportion when the process is under control. So it's our population proportion that we're looking for. The upper limit, just like before, is 3 plus 3 of the standard error from the center line. And then the lower limit is minus 3 of the standard error from the center line or from the mean. Remember, the center line is just that. It's not the mean, but it's really that population proportion. So here we've got an example. We have our population is expected to have a defect rate of 5%. We take 6 samples of 500. So remember, when we're looking at proportions, remember our population samples have to be sufficiently large. So here we took 6 samples of 500, and our sample proportions are as follows, you can see below. And we want to construct a p-chart and plot the sample proportions. So let's look at that formula again. So remember, we're told our p is 5% or 0.05. And remember, our standard error for the sample proportion is the square root of p times 1 minus p divided by n. Okay. So if we crunch that out, remember p is 0.05, n is 500. So if we crunch that out, we get our upper limit as 0.05 plus 3 times that formula is 0.079. Now, if you get an upper limit greater than 1, then just reset it to 1. Remember, proportions can only fall between 0 and 1. So if we get an upper limit greater than 1, we'll just reset it to 1. And then we remember our center line is that 0.05, and then we can calculate the lower limit. Now again, let's jump over to Excel and look at this in Excel. All right, so I'm going to jump over to the defects tab, and here again we have our data, our 6 samples and our sample proportions, and we can calculate our lower limit. We know our center line is 0.05, so we can go ahead and fill that in all the way down. And then my upper limit, we're going to go ahead and calculate that too. So remember, our lower limit here is going to be equal to p, which is in this case 0.05, plus 3 times, now here I'm going to need to open my parentheses, the square root of, open the parentheses, now I'm going to have to open a second set of parentheses, so this is getting a little confusing here, p 0.05 times 1 minus p, which is 0.05, close those parentheses, close a second set of parentheses. Notice how they changed colors. So now I've closed the green and the purple parentheses. So I've closed the parentheses around the numerator. Divide by n, which is 500. I'm going to close those red parentheses, and now I'm going to close the black parentheses. And whew, I hope I've got all this formula in here correct. Let's see. Oh, it found a typo. Let's see. Let me go ahead and accept their correction. And oh, look, we got 0.07924, which is exactly what we were hoping to get. So let's drag that all the way down. So let's go over here and calculate our upper limit as well. So our upper limit is p of 0.05 plus, remember we used minus sign over here, plus 3 times the square root of, let's enter our numerator here. So we've got 3 times the square root of, I've opened one parentheses, I'm going to open a second parentheses, 0.05 times 1 minus 0.05, close that parentheses, close the second parentheses, divided by 500, close that parentheses, close the next parentheses, I think, oh, let's see, oh, yay. Oh, and goodness, I must have entered something wrong there. Let's see. Oh, I see what I did. I put 5 instead of 0.05. Goodness, there we go. Now we get 0.079. 7, and oh, see here again, I messed up. My lower limit was supposed to be subtraction. There we go. Now we've got it all. As my father-in-law would say, now we're cooking with gas. So just to note, I had my lower limit formula incorrect. You can obviously tell I'm doing this live. The lower limit is P minus 3 times the standard error, and the upper limit is 3 plus the standard error. So now that we've got all of our numbers in here correctly, we can graph these. So again, I'm going to grab all of the cells between B1 and E7. And I'm going to insert my line chart. Again, I like the chart with markers. And here I can see now, notice that, this chart is definitely it's trending upwards and it's out of control. So we can already see that the defect rate is out of control and it's getting worse. Notice how the line is trending upwards. So this tells us, we need to stop production now and fix this before it gets any worse, because our defect rate is too high. It's much higher than 5%. Now, we didn't do the paint. I'm not going to do the paint one with you, but if you notice in your book on page 244 or example 7.11 in your textbook, they go over calculating a control chart using this paint worksheet right here. And so I would encourage you to go ahead and try this one on your own. They give you what the chart should look like in the textbook, and go ahead and practice that one on your own before you start your homework for this chapter.